So I saw these two very interesting problems. I mean, these were videos recommended to me on YouTube on the questions that appeared on GATE, and I thought I'll discuss this in this lecture. Two problems, and I think which is very useful for you guys as well, because it involves sampling and AC to DC conversion, which we will be discussing in the next upcoming lectures. Well, let's say you have a continuous time signal, which is band limited, meaning its Fourier transform is contained between, in frequency domain, if you take its Fourier transform, or its energy, or if it's energy signal, or its energy is contained between minus B and plus B, where B is the bandwidth of the signal. Now, in the sampling process, normally if I say that I want to sample the signal, what do you do? Mathematical operation is that you multiply your time domain signal x of t with a impulse train. A train of impulses, you multiply it with your input signal, then you get a sampled signal. Okay, so that's what we call a sampled. That's mathematically the sampling process. The question that was asked in this GATE was that the impulse train is not just a regular impulse train, wherein you have one impulse at origin, and from there onwards, every impulse repeated at intervals of TS, or TS is the sampling interval, TS seconds. It is said that the whole impulse train is delayed by tau seconds. So your impulses, each impulse is delayed, the periodicity will remain the same. So I can simply, instead of showing this as 0, since they are all delayed by tau seconds, so I can show this as tau. This will be tau plus TS. This will be tau plus 2 TS. And this will be tau minus TS. This will be tau minus 2 TS and so on. Okay, so it's delayed like this. Now, I'm not sure about the exact question, but let's assume that your sampling frequency Fs is greater than 2B. Or I can say your sampling interval is less than 1 by 2B. Right? This is the Nyquist criterion. Your sampling frequency should be greater than 2 times the maximum frequency of the signal, where if maximum frequency refers to the positive frequencies. So it's 2B. And let's assume this condition is met. It was given. Now, I'll take this sampled signal and pass it through an ideal brick wall filter with a bandwidth P, same as the input signal bandwidth. A brick wall filter is flat. Its gain is unity in the region, passband region. And then what should be the output Y of t? Will you get X of t as it is, or will you get X of t minus tau? First, the basics of sampling process. If let's say let me take a signal whose bandwidth, which is like this, it's band limited, which is before sampling. After sampling, how do you think the spectrum will look like? What difference? I mean, let this be the X of t. Let this signal be X of t multiplied with P of t. Yes. So one of you asked, what is this brick wall filter? Why am I passing it through a brick wall filter? So this brick wall filter is a reconstruction filter. You want to reconstruct the continuous time signal from its samples. Okay. So that's why it's actually a reconstruction filter. It's an ideal reconstruction filter wherein it can perfectly get your continuous time signal back. The question is, will I get the continuous time signal X of t back or X of t minus tau, because I've delayed my sampling train by tau seconds? That was the question. So I'll come back to this question now. Let's look at this. The Fourier transform of X of f, it's a band limited signal which is limited between minus B and plus B. What do you think? How does the spectrum of Fourier transform of the multiplied signal look like, the sampled signal? How will it look like? Right? It will be just this guy, the main signal, which will go from, see guys, this is for a real signal, it will be symmetric around the origin. So this will be 0, B, minus B. It will be shifted by what? What will be yes, there will be multiple copies, but what will be the frequency spacing? I mean, let's say this is the origin. The second, what will be the center of this guy? By what units will it be shifted? 1 by TS or Fs. Fs is the sampling frequency. So it will be shifted by Fs units. So this will be minus fs, this will be 2fs and so on. You can intuitively, mathematically see it this way. You take a signal x of t. In time domain, you are multiplying it with a pulse, with a impulse train p of t. So the signal in time domain will look something like this. K equals minus infinity to plus infinity, delta of t minus kts. In frequency domain, multiplication in time domain is convolution in frequency domain. So your x of f will be convolved with the Fourier transform of this. The Fourier transform of an impulse train is also an impulse train with an amplitude of 1 by ts. So that will also be an impulse train where k goes from all minus infinity to plus infinity. Delta of f minus, here it will be kfs, where fs is 1 by ts. So when you convolve it, x of f convolved with delta of f minus kfs is nothing but x of f minus kfs. It will be just frequency translated versions of x of f. So you will get summed over k equals minus infinity to plus infinity, x of f minus kfs. So that's what I've shown here. This is x of f, this is x of f minus fs, this is x of f plus fs, this will be x of f minus 2fs, and so on. It will extend on all sides. Now look at this spectrum. If I pass it through an ideal brick wall filter of bandwidth b, right? The brick wall filter's gain is 0 outside the filter. Its passband gain is 1. What do I get out of this? If I pass this signal through an ideal brick wall filter like this, what should I get at the output of the brick wall filter? Right? I'll get the same signal because x of f, you will get the same signal. All those copies of the signal, those copies are called images. Okay? All those copies will be gone because that will get filtered out. The low pass filter will filter out all those things and you will be left with only this copy. So you're getting x of f back. The inverse Fourier transform of x of f is simply x of t. So your x of, maybe there will be some small scaling factor. Let's not worry about that. You get the signal x of t back. Okay, completely intact. On the face of it, it might look like a very simple theorem, right? So it's just, it's mathematically, it all makes sense. But remember, in 1930s, even when digital electronics didn't exist, these ideas were thought of by Nyquist and Shannon. Okay, so it's a great idea at that time. This is the idea why we are able to, we are able to store songs and videos. Okay, because the ideally songs, videos, these are all continuous quantities. Even if I want to store a 10-second song, how many samples are there? If I want to store it digitally, I will need infinite memory, right? It has infinite timestamps from 0 to 10 seconds. But sampling theorem tells you don't need to store all infinite samples. Just store only finite samples. As long as you meet this Nyquist criterion, which is fs is greater than 2b, okay, just store finite number of samples. What is the finite number of samples? 10 seconds divided by the sampling interval. If you store these many samples, that is enough. From these finite samples, I can completely reconstruct my continuous time signal back by doing some mathematical operations. And that happens to be a reconstruction filter in this case. Okay, that's why it's a very powerful theorem, right? You just have few samples, right? You just have very few samples out of infinite samples. And I'm able to reconstruct my signal back from those few samples. So it's a brilliant theorem thought of by Shannon and Nyquist way back in 1930s and 40s. Okay, that's why it's a great idea. So you get your signal x of f back. Now, let's consider what happens when I sample it by delta of t minus tau minus kts. Instead of delta of t minus kts, now I'm going to delay it by tau seconds and sample it. What do you think will happen to this? Just let me give you some intuitions. Let's probably use this waveform here. Let's look at this signal. I'm just directly, again, all Nyquist criterion is met and all that. So you can assume that. So if let's start with 0, t, ts, 2ts, minus ts, minus 2ts, and so on. If I shift this waveform by, say, ts seconds, just by ts seconds, what will happen to this impulse train? See, it's extending in infinite in either directions. So if I shift this waveform by ts seconds, what happens? Nothing, it remains the same, right? The waveform remains the same. If you shift it by ts second, it remains the same. So using that logic, if I say I'm shifting my sampling instances by tau seconds, do you think anything should happen? Anything different should happen? We just argued that if tau equals ts, we are saying that nothing should happen, right? I mean, what if something is happening for tau, for some values of tau, we should see that reflected for all values of tau, right? So that's the important point here. The point is that because it's, you can see, for example, if I shift by tau equal to ts seconds, the impulse train remains the same. Whether you shift it by plus ts or minus ts, you shift it in this direction by ts seconds, the impulse train remains the same. And when you multiply it with this input signal, the Fourier transform will also remain the same. So therefore, you should see no change at all. But okay, let's show mathematically what's actually happening. Okay, let's do that. And so I've just said by intuition, you should expect nothing should happen, right? I shifted by ts seconds and see that nothing happens. The impulse train remains the same. So sample signal should also remain the same. But let's see what happens mathematically. If you shift your signal in time domain by tau seconds, the Fourier transform will have to multiply it by e power minus j 2 pi f tau. Okay, if you shift your signal by tau seconds, your Fourier transform gets multiplied by tau seconds. Is it plus tau or minus tau? Is it plus tau or minus tau? It is minus tau, right? Minus, yes. So you get, this follows from your synthesis equation, right? Your x of t will have a Fourier transform of x of f e power minus, e power plus j omega t dt, d omega, or j 2 pi f t df. So from that, if you substitute t minus tau, you will get that. I'll leave it as an exercise, but it's a very, I mean, you'll find this proof everywhere on the internet. So I'll leave that. So if I shift it, you get this expression. So what happens here is that the Fourier transform gets multiplied by this term. So each impulse, see here, but this Fourier transform for impulse train is also an impulse train. So you will only, the Fourier transform will contain only impulses, and I'm multiplying it with a term e power j 2 pi f tau. So each impulse gets multiplied by a complex number. So right, if I'm multiplying this with an impulse signal, so I can write it this way: summed over minus to plus infinity 1 over t delta of f minus kfs times e power minus 2 pi kfs tau. So if you see, right, each impulse, the kth impulse gets multiplied by e power j 2 pi kfs tau. I can write this one as this way: delta of f 1 by ts plus 1 by ts summed over k not equal to 0. I've removed that delta of f term times delta of f minus kfs times e power minus j 2 pi kfs tau. So now if you see, right, this term, the DC term, remains unaffected by the delays. Okay. So therefore, now if I'm going to take this signal and convolve it with x of f, that's what it's happening in frequency domain, right? I'm multiplying it in time domain. So I should convolve this delayed signal with my delayed signal Fourier transform with my input signal Fourier transform. If I convolve it, I will get x of f as it is plus 1 over ts k not equal to 0 delta of, this will be, you will get multiple copies or images of your input signal. Okay. Each image signal will be multiplied by a complex number. Okay. Each image will be multiplied by some complex number. Now you guys can quickly verify here. What happens when tau equals ts, which is equal to 1 by fs? What happens? This becomes e power minus j 2 pi k. What is e power j 2 pi k? Plus 1. So it has no impact. That's why I said when tau equals ts, it's like it does nothing. You can see that here. But for any other finite value of tau, this term, the main band, the band of interest, which we will call it as the zeroth Nyquist band or the Nyquist band, does not get impacted at all. Okay, this doesn't get impacted. Other bands gets multiplied by some complex term, by a complex number. This is just a single complex number. Okay, so if I pass this through a brick wall filter with a bandwidth of b, I will get this term as it is at the output. So x of t will come at the output as it is. So there x of t will not be shifted by any delay. So that's a very interesting problem. I thought I'll discuss this here. I mean, signal processing engineers, immediately when I saw the question, it made a lot of sense, but I'm just showing it mathematically to you guys. At some point, when you visualize, picturize a signal as a sinc interpolation, brick wall filter is like a sinc function in time domain interpolation. You can, even without going through the math, you can see through that. But since you guys are just in your third, fourth years, I'm just trying to convince you using mathematics. That's it.